Okay, here's a little test of the latest and probably last design of the SmartFlag sensor. What we have here is a DC motor that is driven by those cups, which generates a voltage. That voltage directly relates to the actual wind speed from any direction. There's a voltmeter down there at the bottom of the stand that I don't know if you can read the digits on it or not. There's also a little kestrel meter reading the wind speed. And it looks like a wind speed of about 2 miles an hour. It varies somewhat. But the meter, the voltmeter, we got a peak of about 9 miles an hour. The voltmeter is varying anywhere from practically nothing up to about 3.2 millivolts. The moment arms on the cups are not long enough. I initially set this up with 12-inch moment arms, cut it down to 6. And the reason being is I felt that the anemometer was moving before the vane could react. The voltage coming off the anemometer, like I said, corresponds to the actual wind speed. That voltage is then applied to the vane sensor, which converts it into an angle. So the voltage is actually directly related to what the bullet deflection would be on the target. In other words, the angle change near the null, which would be the lowest voltage setting, will have the maximum rate of change. When the vane swings to 90 degrees, it has very little rate of change as far as angle, but it allows the maximum voltage coming off the anemometer. So when we're near the null, we have very little voltage from the anemometer, but its rate of change is at the maximum rate. When the vane swings around to a 90-degree angle, we have the maximum voltage available from the anemometer applied to the 90-degree angle, but the rate of angle change is very, very minute near 90 degrees. So it actually duplicates the effects of the wind both with speed and angle. I'm going to lengthen the moment arms back out on my next little trial, but based on the initial test with a 12-inch moment arm rather than the 6-inch moment arm, it does appear to be able to work down to a sub 1 mile per hour wind. I changed some of the linkage assembly on the vane sensor because the vane was not turning below 1 mile an hour, so I didn't want the voltage working below 1 mile an hour. But now that we've got the vane working below 1 mile an hour, I'll lengthen those moment arms back out. That's all we got today. I'll let it run a little bit. Hopefully you can see those meter readings change. But the neat thing of this is it actually compensates for the actual angle effect as well as the wind speed effect. So we have a true bullet deflection sensor after all these years of fooling around. It absolutely mimics the wind's effect based on angle and speed. And of course it's combined to a simple voltage output. One other thing, we will show you the back end adjustments. Don't know how well you can see those, but anyhow, we've got that big old black knob to the left at the top is the way we adjust the sensitivity of the flag in relation to the other flags. there's a little hole towards the middle and the bottom right. That is a, so to speak, factory adjustment, just to allow you to zero the device so that the vane is zero, etc. And there's a little test jack to the right of the knob. That's where we input a reference voltage. Doesn't matter what it is, just, you know, a DC voltage like a 1.5 volt battery or something like that. That way we can read the output of the sensor in relation to any other sensor and adjust the scalability so that you know, the first sensor is worth more than the next one, and the next one's worth less, and the next one's worth less, etc. But we have to have a standard voltage to set the output of these. Pretty cool.